So, line segments, we will quickly go over the vector notation and then we can move on to vector functions. When we first started 12.5 equations of lines and planes, I started with the 2D case and then moved to the 3D case with the line. And that's how we derive the parametric form, symmetric equation, all that fun stuff. But in terms of finding that parametric form, what was the first step? Maybe 2D or 3D. I said we need something that is very important, especially in 3 dimensions, to represent a line. 3 dimensions. The directional vector. For some reason, a question on direction vectors always answered by Charlie. I don't know why. Direction vector. If you recall, in order to represent a line, we started with a point right there. That is the known point x0, y0, z0. And another point x1, y1, z1. Known point over here is my direction vector. A, B, C, I believe we call that V. Yes, the direction vector that we choose is parallel to that bad artistry. I called this to be R0. Oh, yes. And over here, I mentioned, well, since that is parallel, any scalar multiple of V can be used there. Agree? Okay. That scalar multiple was TV or VT. Good. Using this, we found the resultant and wrote it as R0 plus VT. And that was our guiding equation to find the symmetric equation, the parametric form of the line, etc., which we then extended to a plane. We can't simply rely on a direction vector for the plane because easy question. What do we need instead? Start with the letter N. End with the letter L. Something I'm not. To get the joke, something I'm not. Yeah. No. Jeez, I'm not. I like to think that way. So we need a normal vector in terms of a plane. Good. Now, that point, I'll call it x1, y1, z1 point vector. You know, I say tomato, you say tomato, but we're talking about the same thing. What is a good thing about having a parametric form or something in terms of t? Why did we even bother? Even though we used a straight line, I mentioned we need the parametric form for a reason. Why? Particularly in 3 dimensions. It helps us trace the line by varying the value of t. Now, as I change t, starting point, this way, that way, and especially in 3 dimensions, when you have a funky looking curve, you can't simply use a function to represent that because our knowledge of functions are limited to 2 dimensions. Yes. When I extend it to 3 dimensions, it becomes a problem. Another case, if you have a plane, to explain that plane properly in 3 dimensions, it's easy, but if you want to break it down to lower dimensions, you've got to know line 1, line 2, line 3, line 4, too much, yes? In this case, I'm simply looking at a segment, and that segment is represented by the vector. I have TV, but I can rewrite it in terms of the point. What is that point?
Where TV is TA, TB, TC.
Ah, TA, TB, TC, sure, but in terms of those 2 points.
Oh, just what? X, yeah, X1 minus Y1. X1 minus X0. Y1 minus Y0. Z1 minus Z0.
Good. And I can vary this, rewrite this as R0, which simply is X0, Y0, Z0, plus V times X1 minus X0, Y1 minus Y0, Z1 minus Z0. Oops. Math, T. Good. Now, if I combine the terms, this would simply be X0 distributing T, X0, Y0, Z0, let me not skip a step. Get it? Let me not skip a step. Tx1 minus Tx0, Ty1 minus Ty0, Tz1 minus Tz0. Good. Combine the components. X0 plus Tx1 minus Tx0, Y0 plus Ty1 minus Ty0, Z0 plus Tz1 minus Tz0. Good. Combine X0, Y0. 1 minus T times X0 plus Tx1. 1 minus T Y0 plus Ty1. 1 minus T Z0 plus Tz1. Good. That would be the vector notation, the parametric form, etc. I can call this as x of t, y of t, z of t. I have to take it one step further. I can write it as split it back. 1 minus t x0, 1 minus t y0, 1 minus t z0, yes, plus the second term tx1, t y1, t z1. Good. I could have written it, from here to there, just like that. I don't want you to get confused, which is why I didn't skip steps. Here, 1 minus t is the constant. If I took 1 minus t up, I will leave behind x0, y0, z0, correct? But what is the vector x0, y0, z0? It's just R0. That's what I started. Here, T is the constant. If I took that is R1, my bad. Did we use R or R1 in our original derivation? We used R, correct? Yeah, so I'll put R1 here because I wrote the resultant in a different way. The reason I'm using R1 is because I want to represent from 0 to x1, y1, z1 as R1. So I can rewrite this as t multiplied by x1, y1, z1. Good? Yes. And x1, y1, z1 is simply the known point, or the other point. They did the work uses R1, so we can replace that to R1. So what is R1? It is simply origin to the point. That's it. So R equals 1 minus 2, initial point, plus t times R1. Good. So parametric equation of a line segment from x0, y0, z0 to x1, y1, z1. Good. Here's a question. If I want to represent that segment, what are the limitations or bounds for t? I'm going to go with 0 to 1 inclusive. Reason being, I am not referring to a line that is in 3D space. I am simply referring to a segment in 3D space. Particularly the segment is between the vector x0, y0, z0 and the vector x1, y1, z1 reference to the origin. So I'm starting here, ending there. And according to our setup, if t is 0, that will go away because the parametric or the parameter t is going to trace the segment, just like it traces a line. If you start at 0, that term will go away. T is 0, you start at R0. As you increase the value, positive number, why not a negative number? Why can't it go below?
Because our starting point is at x.
Yeah, we're starting here. If it is negative, we're no longer talking about that segment. We're talking about something else. And as I approach 1, this would be 1, 1 minus 1, 0. That term will go away. 1 times R1 ended at R1. Good. So the bounds for t, inclusive bounds, t has to be in 0 to 1, inclusive. Rachel, does that make sense? Hey,
Yeah, it does.
Caleb,